Hashing. Ooh, I love hashing. So like I said, hashing is not listed on the exam objective. So I've added this because it should be there. It might have been an oversight. Or maybe they just assumed that it would be part of this discussion anyways if you were teaching it or writing a book about it. So I've added it in. What is hashing about? Like compared to something like we just talked about with encryption, right? So encryption itself is about taking something that is in plain text, that is human readable, and turning it into something that is ciphertext, unreadable, unless you have the right keys to decrypt. So one thing we ought to know is that encryption is something that is reversible. 100%. Encryption is something that is reversible. You encrypt, you decrypt. You encrypt, you decrypt, right? Hashing is not. Hashing is not reversible. Just something to keep in your mind. So when we hash something, right, we're creating a value out of that. And we can use hashing for many different reasons. And I have a slide to talk about that momentarily. But essentially what happens is when you're hashing, you're creating something called a digital fingerprint of that data, a unique fingerprint of that data at that very specific moment in time. Think about your own fingerprints. They are extremely unique to you, right? And that's what you're doing. You're creating a digital fingerprint of this data, and no other data in the entire world should be able to produce that exact same digital fingerprint, period. Because that fingerprint is unique to that data in question. So when we're hashing, we're taking the inputted data, whatever that inputted data is, right? It could be text, it could be a picture, it could be an operating system image, it could be anything, folks. You can hash anything and get a digital fingerprint of that item. So you're taking whatever that input is, and it's an arbitrary size, right? It's whatever the size it is. And when you hash it, you're creating a fixed size digital fingerprint that is just a string of characters, a sequence of numbers and letters like you see down here at the bottom. When you look down here, you're going to see that I took the word CISSP rocks and I ran it through the SHA-3 hashing algorithm using 512-bit. And as a result of that, it produced this digital fingerprint of that. Now, I did this last August. This morning, I decided, you know what? I'm going to run CISSP rocks through a different tool that I have and see if it produced the exact same digital fingerprint. And you know what? It did. So just to tell you that when you do this, right, you are creating that digital fingerprint. So if any of you grab a tool, SHA-3, 512, you go with CISSP rocks, you should get this. So our hash function, in this case being SHA-3, produce this output. Okay, so there's many different hash functions. You get MD5, you got SHA-1, you got SHA-256, then you got SHA-3 of 224, 256, 384, 512, okay, variations. And the thing is that depending on the hashing algorithm you use will determine how long the output is. So this was SHA-3, 512, and therefore I've got 128 characters. But if you use something like MD5, you can see that you have, it's only 128 bits, but it only produces 32 character digest. SHA-1 produces a 40 character digest. SHA-256 produces a SHA-256 64 character digest. And then SHA-3 and these different options, you got everything from 56 characters, 64 characters, 96 characters, up to 128 characters. Right? So obviously, the further down you go in this list, like SHA-3, 512, right, you're getting the, the best protection in modern day environments because you have the latest algorithm in use, which has been modified to fix any vulnerabilities in previous algorithms. And it's also producing a really big fingerprint when it's all said and done. So it doesn't matter, okay? What I'm trying to point out to you is it doesn't matter if it's a single word, like we have here, CISSP rocks, or a Word document that has 1,000 pages, okay? In the end, the digital fingerprint would be the same length. Whether it's a single word you were hashing or in a 1,000-page document, the fingerprint would be the same length. If it's SHA-3 512, it's 128 characters. If it's SHA-256, it's 64 characters. If it's MD5, it's 32 characters. Right? So it's a fixed size output based on the hashing algorithm and the number of bits that you used as part of that hashing algorithm. Okay. Now, the thing about hashing is that any tiny, itty bitty little change produces a totally different hash. Okay. So what I also have done is I've taken the word CISSP rocks, but I did a lowercase on the C. I lowercased the C. There it is. Okay. I lowercased the C. You see that? This is the hash for CISSP rocks with a lowercase c. Compare the two. They are completely and wildly different from each other. That's the power of hashing. Tiny little changes produce wildly different results, giving you the ability to compare things. So let's say you had a 1,000-page Word doc and you ran it through your hashing algorithm. It gave you the fingerprint. Now you can store that fingerprint, right, wherever you want, and the document wherever it needs to be stored. They could be stored together, it doesn't matter. The idea here is that in the end, if I go access that document and I want to know if that document has ever been changed, then what can I do? Rerun the document through the hashing algorithm, the same one that was used to create the fingerprint. If I run it through it and I get the same result, that means the document wasn't changed. Integrity check right there. Verify the integrity. Okay, but what if the result was different? Then I know the document has been modified. Even if somebody simply added a period or a space somewhere in the entire document, I'd have a wildly different hash value at that point in time, knowing that somebody's changed this and it shouldn't have been changed. So one of the things that hashing gives us is integrity checking. Right. So what I've done a while back is I took a screenshot of this page, not this page. I took a screenshot of this page and I ran the page, the screenshot, through a hashing algorithm, and this is what it produced. So this is a SHA-3 512 hash of the slide without this information there. And that's what it produced. So it's based on the characteristics of the screenshot I provided to it. Now, the only problem with that is if I try to take a screenshot again and do it, if my screenshot is not the exact same size as the original in the exact same way, then I'm going to get a different hash value, right? That's the only thing. So it's really hard to produce this exact same hash with a screenshot again, only because it's a screenshot in that case, right? I'd have to have the exact same screenshot and run it through the hashing algorithm. But there you go, right? So let's talk about now common uses, because we already know one of them, and that is to provide data integrity verification. So we've already talked about that. That's already out of the way, right? What do? We can hash anything we want, and then later on down the road, hash it again. And if the hash values are the same, then the data integrity is there. If the hash values are different, then the data integrity is not there. Okay, so another very, very common use today is password storage. Really? Absolutely. Right. We do not today encrypt passwords. Why do we not encrypt passwords? Because encryption is reversible. So if encryption is reversible, that means if anybody steals my password database and they have ability to get the decryption key, or even if they don't have the ability to decryption key, then they could possibly brute force that encryption algorithm find flaws in that and reverse, right? They could reverse the encryption of that database. So the better option is to hash your password databases, because hashing is not reversible. When you hash something, it's not reversible. Now you might be saying, well, wait a second. But if I hash my password, then the original password's still in plain text and I have a hash of it. Okay, no, in this case, we actually hash the password so the plain text doesn't exist anymore. That's how we use it for password databases. So here's the thing. When you now, let's say, are creating an account, you create the username, you create the password in plain text. When you submit it for the account creation, what'll happen is the system behind the scenes will not store the plain text. It will hash it first with whatever hashing algorithm is being used, and the result of that hashing algorithm is stored in the password database, and then the plain text is deleted. So that means the plain text is not even available. And now every time you authenticate, you put in your password, and then your password is going to be taken, converted into the hash, and then the hash is going to be compared to what's in the database. If the hash is the same, it means you typed in the right password. If the hash is different, it means you typed in the wrong password. And there you go. So now if somebody steals the password database, all they have is a bunch of hashes. That's all they have. A lot harder now for them to figure out what the passwords are. Now, if you're still using weak passwords, common passwords, dictionary passwords, obviously they're going to figure it out, because cyber criminals have something called a rainbow table. And a rainbow table is what? It's a table of plain text passwords and all their hashing variations of it. So they'll have, for example, the word password in the rainbow table. And then they'll have the MD5 hash of that, the SHA hash of that, the that hash of it, the that hash of it, and so on and so forth. So then what they do is when they get their password database, they then use their tools to compare all the hashes they have now to that hashing list they have. And if they find one that matches, then they know it is that particular password. So the way to, circumvent that is to make sure what? We still use strong passwords. Strong, unique passwords. So if the database is stolen, they can't easily go through it and find the right hash that is associated with a certain password, because they would not have your password in the database if it's a strong, unique, complex password. They wouldn't have it because they wouldn't be able to produce a rainbow table with all the various combinations that exist in the entire world. I mean, eventually you might be able to, sure. At that point in time, right, we're definitely going to have to use passwordless authentication, biometrics, right, USB keys, different things like that at some point in time, because when they figure out how to create an entire database of every single word, combination, letter in the entire world, up to 64 characters long, let's say, every combination of everything, 64 character long, produce every hash that goes with every one of those, I mean, then passwords are going to be useless to us. Because then they'll have it in a database that can be searched through with very, very fast computers, right? So, but right now, password storage, hashing, that's the right answer. Digital signatures. Okay, the thing about digital signatures is we are trying to send information to somebody, sign it with our private key, right? So that way they can decrypt it with the public key, and then it can verify that it actually came from the person. Remember, digital signature is not about confidentiality. It's about authentication, verification, that is the actual sender of that message. So you take your private key, you encrypt something, you send it to me, I decrypt it with the public key, and because I'm able to read the message and it makes sense, and I was able to decrypt it, then that means it really came from you, because you're the only one who should have the private key. Okay, here's the thing though. We cannot encrypt large amounts of data with what? With the private key. Because remember what we said, asymmetric, public-private key pairs, very computationally intensive. So since they're very computationally intensive, what does that mean? It means I cannot use it to encrypt an email and send it to you, a large email with an attachment as an example, right? Very computationally intensive. Can't use the asymmetric keys for that. So I cannot take my private key and sign it with my private key and send it to you, because the problem with that is the computational power involved. If I wanted to send a massive amount of data to you, right? And I wanted to sign that. Well, I can't encrypt all that data with my private key and then send it to you, because again, computationally intensive. So what we do instead is we hash whatever it is we want to send you and get a digital fingerprint. Now, we leave it in plain text. So if I want to send you an email as an example, and I want to sign the email, or I want to sign data that I'm sending to you, right? What can we do, right? Take the information, take whatever it is, and hash it first. Because when I hash it, hashing's fast, hashing's efficient, hashing's effective, okay? We can produce these fingerprints very, very fast. So I have a 1,000-page document I want to send you, but I want you to be able to verify that it came from me. So I'll hash it first, create a digital fingerprint, and then I'll use my private key to what? Encrypt the hash. Because if it's only 128 characters, encrypting that with my private key, not a big deal, right? Not a big deal. Great, perfect, okay? So now the hash is encrypted with the private key. So I send you the 1,000-page document with the encrypted hash. Now you get the 1,000-page document with the encrypted hash and you decrypt it with my public key, and now you know that I am the actual sender of this document and nobody else actually sent it to you. It really came from me. Now you might be saying, but wait, we should have encrypted the document too. Yeah, what would we use to encrypt that document? Symmetric encryption, right? So let's just add a little bit more to this. Okay, let's go back to the thing. I want to send you a 1,000-page document. So what do I do first? I encrypt it with the symmetric key. Encrypt it with the symmetric key first. Okay. Now I take a hashing algorithm and I hash the encrypted document. And now I have a hash that goes along with it. So I have the encrypted document and the hash now. Now I take my private key and what do? I encrypt the hash with the private key to sign it. Then I send you the encrypted document, symmetrically encrypted document with the hash that's done with the private key, the digital signature. You get it. Now you decrypt the hash with my public key. You know now this encrypted document really came from me. So if anybody else intercepts it, doesn't matter because they can't decrypt that. You're the only one with the symmetric key that can be used to decrypt that. Boom, there you go. Cryptography in action, right? But there's the digital signature. We can use hashing for digital signatures because it's just too computation intensive to actually hash the full data we want to send. Blockchain and cryptocurrencies. So in the blockchain, we need a way to verify the integrity of all the blocks of data that are in there. So we use hash values, hash functions to do that. So each block in the blockchain contains the hash of the previous block, creating an immutable chain that is resistant to tampering. It's pretty cool. And then file and software verification is another good example. So somebody like Cisco puts their operating systems up on their website and you want to download the operating system. How do you make sure that that software is from them? How do they make it's verified, that it hasn't changed, hasn't been tampered with? Well, their developers are going to turn around and create a hash value and put the hash value with it. So now you download the document and then you hash it on your own machine with the right hashing algorithm that they said they used. And then you compare the hash with the one listed on their website. And if it's the same value, then you know when you downloaded that operating system, it's still perfectly fine. It hasn't been tampered with. And then you can go ahead and use it. But if the hash value is different, then you're going to know that, the software is not what it's supposed to be. And therefore you're definitely not going to want to use it. And maybe you should contact Cisco in that case. So